Jupiter isn't what you learned in school. For decades, we called it a gas giant, a massive ball of hydrogen floating in space. But when NASA's Juno spacecraft got close enough to actually measure what's inside, scientists discovered something that doesn't fit any model we had. Jupiter has a core, but it's not solid. It's fuzzy. That's the actual scientific term they're using. Fuzzy. The core is dissolving into the layers above it, mixing rock and metal with liquid hydrogen in ways that shouldn't be possible. And the deeper Juno looked, the stranger it got. Jupiter's magnetic field is lopsided, 20,000 times stronger than Earth's, and nobody can explain why. This isn't just surprising, it's rewriting everything we thought we knew about how giant planets form. Subscribe to Space Aquarius and let's begin. Here's what makes this so unsettling for planetary scientists. They've spent their entire careers building models of how our solar system came together. Jupiter was supposed to be the anchor, the first planet to form, the one that shaped everything else. If we don't understand Jupiter, we don't understand how Earth got here. We don't understand why we're here. For most of the space age, Jupiter's interior was basically guesswork. We could see the storms, the famous Great Red Spot, those beautiful bands of clouds. But what lay beneath? Complete mystery. Scientists had two main theories, and they were pretty confident one of them had to be right. Either Jupiter had a dense, rocky core at its center, or it had no core at all. Just layers of gas getting denser and denser all the way down. Both theories made sense. Both fit the math. But here's the problem. Both theories were wrong. But what Juno found when it finally got there changed everything. The data coming back didn't match either theory. Instead, it revealed something nobody predicted. Something that's forcing scientists to question the basic principles of planet formation itself. Jupiter isn't a gas giant at all. It's a liquid planet. And not just any liquid, it's a liquid metal planet. Let me explain what that actually means, because it sounds like science fiction, but it's real. When you descend into Jupiter, past those swirling clouds we see in pictures, the temperature and pressure start climbing fast. About 600 miles down, something remarkable happens. The hydrogen gas becomes so compressed by Jupiter's own gravity that it transitions into a liquid state. Not like water, this is hydrogen staying liquid at temperatures over 1,000 degrees Celsius because the pressure is so intense. This creates the largest ocean in our solar system. Not water, but liquid hydrogen, stretching down for thousands of miles. And we're not done yet. Keep going deeper, and the pressure gets so extreme that the hydrogen enters a state that doesn't exist naturally anywhere on Earth. The electrons get stripped away from the atoms, and the hydrogen starts conducting electricity like a metal. Liquid metallic hydrogen. It sounds impossible, but it makes up most of Jupiter's interior, somewhere between 75 and 90% of the planet's total mass. Think about that for a second. Jupiter is essentially a ball of liquid metal the size of 11 Earths, spinning once every 10 hours, generating a magnetic field so powerful it creates radiation belts that would kill any spacecraft in hours. Now here's where it gets really strange. At the very center of all this liquid metal, scientists expected to find either a compact rocky core, maybe 10 to 20 times Earth's mass, or nothing at all. What Juno actually measured was something in between, something they're calling a fuzzy core. The core isn't a solid ball. It's not clearly defined. Instead, heavy elements, rock, metal, ice, are spread out across a huge region maybe half of Jupiter's entire radius. These materials are gradually blending into the metallic hydrogen above them. There's no sharp boundary, no clear line where the core ends and the liquid metal begins. It's all mixed together in this diluted soup that extends for thousands of miles. This shouldn't be possible. Gravity should pull the heavy stuff down and keep it there. You shouldn't get this kind of mixing. It's like finding out Earth's iron core is somehow scattered throughout the mantle. It violates basic physics. Scientists scrambled to explain it. The first idea was a giant impact. Maybe early in Jupiter's history, another massive planet 10 or 20 times Earth's size slammed into Jupiter with such force that it shattered the core and mixed everything up. It's a dramatic explanation, and it would work. Except it doesn't. Researchers ran thousands of computer simulations of these massive collisions. They tried different sizes, different angles, different speeds, and yes, the impacts would temporarily create a fuzzy core. But here's the problem. It doesn't last. Over time, maybe a few 100 million years, gravity wins. The heavy elements sink back down. They reassemble into a compact core. The simulations showed this happening every single time. But Jupiter's fuzzy core has been there for over 4 billion years. It's not temporary, it's stable, which means the giant impact theory, as appealing as it sounds, probably isn't the answer. So what is? The current thinking is that Jupiter's fuzzy core isn't the result of destruction, it's the result of how Jupiter formed in the first place. As the planet grew, heavy elements didn't just sink to the center and stay there. They partially dissolved into the surrounding hydrogen and helium, creating gradients instead of layers. And here's the key part. Jupiter's interior isn't fully convective. On Earth, our mantle churns and mixes constantly. But large parts of Jupiter are stable. They don't mix. That stability allows these gradients to survive for billions of years. And Jupiter isn't alone. When scientists looked at Saturn using data from the Cassini mission, they found the same thing. Saturn also has a fuzzy core. 2 giant planets, both with this strange diluted structure. That's not a coincidence. That's not a random collision. That's telling us something fundamental about how giant planets form. This matters beyond our solar system. We've discovered thousands of exoplanets, planets orbiting other stars. Many of them are gas giants, some even bigger than Jupiter. For years, we've been modeling these planets using the simple layered structure we thought Jupiter had. But if Jupiter and Saturn both have fuzzy cores, then our models for all those distant planets are probably wrong too. Take hot Jupiters, gas giants that orbit incredibly close to their stars. They're puffier than they should be, hotter than our models predict. Scientists have struggled to explain why, but if you factor in fuzzy cores, if you account for these gradients of heavy elements mixed throughout the planet, suddenly the numbers start making more sense. The fuzziness changes how these planets cool, how they evolve over billions of years. But the fuzzy core creates another problem, one that's even harder to solve. Jupiter's magnetic field is bizarre. It's not symmetric like Earth's, it's lopsided, with strange patches of intense magnetism and even multiple south poles. On Earth, our magnetic field comes from liquid iron churning in the outer core. It's relatively simple, relatively predictable. Jupiter's field should work the same way. Liquid metallic hydrogen spinning rapidly should generate a strong, organized magnetic field. And it does generate a strong field, the strongest of any planet. But it's not organized, it's chaotic. Scientists hoped the fuzzy core would explain this. Maybe the mixing of heavy elements creates unusual flow patterns in the metallic hydrogen, and those flows generate the weird magnetic field. But when they ran the models, it didn't work. A stable fuzzy core doesn't produce the kind of magnetic field Juno measured. In fact, it often made the predictions worse. So now they're looking at other possibilities. Maybe helium is raining down through Jupiter's interior, literally separating out and falling like raindrops through the metallic hydrogen. That would create different kinds of flows, different patterns of convection. Or maybe the dynamo that generates the field doesn't operate uniformly across the whole planet. Maybe different regions have different conductivity, different densities, and that creates the patchwork magnetic field we see. The truth is, we still don't know. And that's what makes this so fascinating and so frustrating for scientists. Jupiter is right here in our solar system. We've sent multiple spacecraft to study it. We have decades of observations. And we still can't explain how its magnetic field works. But here's why this matters to you, even if you're not a planetary scientist. Jupiter shaped our solar system. Its massive gravity pulled in comets and asteroids that might have bombarded Earth. It may have protected us, or it may have delivered the water that makes life possible. Understanding Jupiter means understanding our own origins. And there's a practical side too. NASA is planning missions to Europa, one of Jupiter's moons, where a vast ocean exists beneath the ice. That ocean might harbor life. But Europa sits deep inside Jupiter's radiation belts, those belts created by Jupiter's powerful magnetic field. To safely send a spacecraft there, to protect the instruments, we need to understand that magnetic field. We need to know what's generating it and why it behaves the way it does. The same goes for future missions to Ganymede and Io. Every mission to the Jovian system has to navigate this intense radiation environment. The better we understand Jupiter's interior, the better we can plan these missions. And Juno's mission isn't over yet. In fact, NASA just pulled off something remarkable that almost nobody saw coming. Instead of crashing Juno into Jupiter's atmosphere like they did with Cassini at Saturn, they're sending it on one final mission to chase down an interstellar visitor. In September 2025, NASA executed a maneuver that changed Juno's orbit around Jupiter. They're using Jupiter's gravity itself as a slingshot, what's called an Oberth maneuver, to fling the spacecraft out toward a deep space. The target? An object called 3I Atlas, an interstellar visitor passing through our solar system. This thing came from another star system, and it's going to pass within 33 million miles of Jupiter in March 2026. Here's what makes this so impressive. Juno was designed to study Jupiter, not to chase comets. But NASA's engineers calculated that with just the right burn at the right time, they could redirect Juno to intercept 3I Atlas's path. They're doing it with only about 110 kilograms of fuel left, just 5% of what Juno started with. That's like driving cross-country on fumes and somehow making it. If this works, Juno will get close enough to study this interstellar object in ways Earth-based telescopes never could. We'll learn what it's made of, where it came from, maybe even get clues about planetary systems around other stars. It's a bonus mission nobody planned for when Juno launched back in 2011. But here's something I didn't tell you at the start of this video. Everything I just explained about Jupiter's interior, the liquid metal, the fuzzy core, the bizarre magnetic field, that's just what we've learned about Jupiter itself. We haven't even talked about what's happening on its moons. because the discoveries Juno made about Jupiter's magnetic field revealed something shocking about Europa's ocean, something that changes everything we thought about where life could exist in our solar system. If you want to understand what scientists found beneath Europa's ice and why it's making them rethink the search for alien life, I will make another video that breaks it all down. But before you go, hit that like button and subscribe to Space Aquarius. Drop a comment below and let me know what surprised you most about Jupiter. Was it the fuzzy core, the liquid metal ocean, or that Juno is now chasing an interstellar visitor? And if you know someone who'd find this fascinating, share this video with them.